Today we start part D of module 2, brute force method. Part D.1, introduction to brute force method. We have some experience using the brute force. In this part, we want to, get a better understanding. It is a simple method, but we try to, get some basic idea using this, simple method. All right, so let's start. Description of brute force method. First, let's look at the properties of brute force method. First, it is a straightforward approach. So you do not need to use any technique. So basically, we just based on our intuition, so we can, use our common sense. So we try to work on the given computing problem directly using our basic knowledge, not necessarily advanced knowledge. So in that way, you can get a, basic solution, starting point, initial solution. Anyway, it is a solution, right? You get some solution. Hopefully a solution, right? Because sometimes, probably many times, even you try to use the straightforward method, you may not be able to find a solution if the problem is very hard. Okay? So the brute force method usually works when the problems are relatively easy. Okay? Yeah. Relatively easy. If the problem is very hard, you don't care about the efficiency of the algorithm. You just want to get a solution. Even if it is acceptable to use brute force method, you may not be able to get it because the problem is very hard. So that could also happen. Okay? All right, so here, you can always apply it to a problem. You can always, here, it's better we say, you can always try to apply, right? Try to apply, but it may not work, right? It may not work. You can try. Okay? Yeah. You can try. Yeah. Usually people try brute force at the beginning. Okay? Yeah. But you have a pretty good chance you get a failure. Yeah. So it's better, more precisely, you can always try to apply it to a problem. Okay? All right. So in general, it is not the best algorithm in general. Yeah. But in some special case, it could be the best algorithm, right? Yeah. The problem is not very hard. The problem is very easy. Even if we just use the brute force method, we can still get the best algorithm, right? Yeah. Actually, we have a good example, right? So look at that. Find the minimum problem. Look at that one. Okay? Here. Find the minimum. Think about that problem. If you look at our solution, do we just use the brute force method? Yes. We compare to the adjacent elements. We do not use any advanced technique. the simple method, straightforward, right? It's the brute force, right? Yeah. But it is the best algorithm because we proved it is optimal. Nobody can improve it. It is the best by the brute force, right? But you can see the problem is very easy, right? Very easy. Yeah. But if the problem is very hard, then don't try to expect to get the best solution using the brute force method. You cannot. If it's a pretty hard problem, you have to apply some advanced technique. Okay? Yeah. All right, so let's continue. Next property. It is usually used as the starting point for more advanced algorithms. Yeah. So that's the usual way we use the brute force method. We know most of the time it cannot give us the best solution. That's true. 99% of the time, the brute force. Yeah. So we can say in that way. Yeah. We can say in that way, 99% of the time, the brute force method cannot give us the best solution. So while we still sometimes we try to use the brute force method, right? It is still valuable. Why it is still valuable? We know we cannot get the best solution from it. But why we still use it? The reason is this. We want to get experience. Experience. We know experience is valuable. Valuable. Okay? When you work on a pretty hard problem, do you have any experience? At the beginning, you're not familiar with the problem, right? You're not familiar with the, environment, what is important. So what is the, good way to solve? You do not have that kind of deep understanding at the beginning. In that situation, the brute force method is a good starting point. At least you can start somewhere, right? You can start somewhere. Yeah. So for that reason, we use it as a starting point. Okay? If we can get a solution, then we are not satisfied with it. We will continue to improve our solution. And hopefully, we can get the best solution sooner or later. Okay? All right. Another property. The efficiency difference between the brute force method and the more advanced algorithms could be huge. How big it is, we have the experience. Okay? Yeah. In our polynomial evaluation problem, we saw it. We saw it. Okay? So when we compare, remember, when we do experiment, when n equals 1 million, right? Yeah. So we did, 2 experiments in our analysis, not in our program. In your program, you get the, empirical experience, right? Yeah, you do empirical analysis in our project number 1, so you have that kind of hands-on experience. Yeah. But in our analysis, mathematical analysis in this testing comparison, remember 5.8 days. In our example, 5.8 days versus 1 second difference. Think about that. Versus 1 second that huge. Okay? Yeah. So we see that pretty clear. Yeah. All right, so that's the basic properties of the brute force method. Next, let us apply it to solve a problem we are quite familiar with. Sorting. We did one recently, right? We did one recently. Selection sort. We have a selection sort. All right? Let us find another different sorting algorithm. Yeah. So let us revisit the problem, sorting problem. Yeah. So this is the problem. Yeah. The question, before we work on that, so let us answer this question. Yeah. Why we need to solve it another time? Yeah. Why we need to solve it another time? We already solved. We have the solution. Why we need to solve it another time? Yeah. All right. So to answer this question, all right, there is one way to view this problem is because our previous solution is not optimal. So for that reason, we have some reason to try another solution, right? So that's one way you can look at this question. Yeah. But here, I want to use a different angle to view this question. All right, so let me describe it, the new view. Yeah. So our view here, let's think in this way. A problem is a carrier, okay, of a set of thinking methods. Look at this way. Think about that. That result in different solutions. When you need to get a different solution, usually you need to use a different thinking method. If you use the same thinking method, you will get the same solution, right? So usually, in order to get a different solution, you have to change your different thinking method. Yeah. All right. The thinking methods are important in our problem solving, right? In our real world problem solving, we rely on many different thinking methods. That's the most valuable things. Thinking methods, very important. Okay, yeah. Not particular solution, selection sort, other sorting algorithms. So we will have many later. Yeah. Not those specific solutions. The thinking methods more valuable. We need those thinking methods. All right? Yeah. All right. But the question is, how do you package, let me use this word, package those thinking methods? We know thinking methods very abstract, right? Can you see it? You cannot. What is the thinking method here and there? Can you see it? You cannot. You can only imagine those thinking methods, right? You cannot view them. Yeah. All right. But thinking methods exist, right? Exist and are valuable, right? Yeah. All right. So here's the question. How do you put large number of thinking methods somewhere together in a package, putting in your brain, right? Put in your brain. Then in the real world situations, you need to use some of the thinking methods to solve those problems, right? Yeah. All right. Carrier. Do you need some carrier, right? Do you need some carrier to hold thinking method? That's good. If there is some carrier, then it is more convenient to, put the thinking methods in some place and, save in your brain. When you need them, you can use some of them. All right? Yeah. Here, a problem is that carrier. A problem, sorting problem. Okay? Let's imagine a sorting problem. Sorting problem can hold thinking method 1, thinking method 2, 3, 4, 5, 6. All right? So you can put that sorting problem in your mind easily, right? After this class, you will never forget the sorting problem. Okay? It is in your mind permanently, right? All right. So that problem would carry multiple thinking methods. And those thinking methods could be useful in your real world problem solving situations. That's our new understanding, new view of it. Okay? All right, so let's use this view to solve this problem another time. All right. A view based on special property. When you have a view, right, can you find a special property in the problem, current problem? If you cannot, it's very hard to solve it. You need to find. You need to carefully examine, do analysis on the problem, and try to explore and get a special property. All right, so here, let's do that observation on the sorting problem another time. This time we try to view differently. Okay? Differently. All right. All right. What is that property? The critical property. We need to dig it out. Okay? The critical property. So let's look at this diagram. Our goal, get all the elements in this array sorted. Then we imagine if it is not sorted, then somewhere, someplace, the ascending order would break. The order breaks somewhere, right? Someplace. Ascending order breaks. For example, here, let's look at these two elements. Their values could be out of order, right? Their values could be out of order if the whole array is not sorted. That is this kind of thing. Order, out of order, this property, this is the key property we want to use to understand this problem. All right. Observation for critical property. We try to get something useful in this step. If the array is not sorted, there must be two adjacent elements that are out of order. Do you think it's true? This probably is true. There must be two adjacent elements out of order. You can imagine if there is no such pair of two adjacent elements out of order, every two adjacent pair of elements are in order, you can easily see the whole array must be sorted, right? If every two adjacent elements are in order, then the whole array is sorted automatically, right? So this property must be true, must be correct, and it is useful to get a new solution here. All right, yeah. Here, this out of order That is the main property we want to study. Okay, yeah. All right. The reference for this solution you can find in this section and page. Yeah. Next, I like to introduce a new concept called inversion concept. Inversion. Okay. From this name, you can guess the meaning a little bit. Here, let me give you the definition of this inversion concept. A pair of elements, A sub I and A sub J. Yeah. Not necessarily adjacent. We don't require two adjacent elements here. So anywhere in the array, element in I position and element in J position, two elements in arbitrary locations, okay, is called an inversion if they satisfy this condition. So what condition? If I less than J, Ij is in ascending order. The subscripts of these two elements, I and J, or the indices, are in ascending order, but their values are in descending order. A of I is greater than A of J. So if that happens, we have one inversion with respect to this pair, this element pair, AI, AJ pair. That's the straightforward definition. All right. So now we will use this concept because the concept will be useful to help us organize our thinking. Yeah. People may ask why we need to create so many abstract concepts, right? When we learn new knowledge, okay? Why we need to learn so many new terminologies, new concepts, very abstract concepts. And we need to spend a lot of time on those concepts. Why we need those things? The reason is very simple. To organize our thinking. Yeah. Organize our thinking. You can think about, without those terminologies, without those concepts, when we try to figure out some very complicated things, it is very hard to organize our thinking. Okay? But when we have those well-defined concepts, terminologies, then we use those concepts. We can organize our thinking to understand a very complicated thing, object. Yeah, object. All right. Yeah. Implement. So here, all right. Before we work on the solution, so let me just look at this property another time. So we try to understand the property better. Okay, if the array is not solid, there must be an inversion. We use the inversion concept to understand the current problem. Okay, helping us organize the idea, thinking. Okay, yeah. So this time, if the array is not solid, there must be an inversion. Okay, we do not need to use a lot of words related to this inversion concept, because after our definition, this inversion simple concept, it holds very rich meaning there. A lot of meaning, a lot of content in this one word, one concept. That's the value we need when we organize our thinking, right? It is valuable. Yeah. All right. let me repeat another time. If the array is not sorted, there must be an inversion. That's true. All right. But we want to move another step forward on this for this understanding. Yeah, we want to improve the same property, but we want to make it easier for us to use. Okay, so we improve. Yeah, we write the sentence to get a new sentence. New sentence is equivalent to the older one, but much easier to use in our implementation steps. All right, yeah, here. If the array is not sorted, there must be an adjacent inversion. Adjacent inversion. Two adjacent elements, that pair form an inversion. Yeah. All right, yeah. You can see improved. Yeah. From arbitrary inversion, improved to adjacent inversion. Is it a better way? Yes, it's a better way. Yeah. Because we change our view from a global view. The old inversion, that's a global inversion, right? You know, arbitrary locations, two elements in the array, global view. Now we get a local view of the adjacent inversion. So that will be better. Yeah. All right. Now we need to solve the problem. When we have an inversion or when we have an adjacent inversion, how do we fix it? We need to fix it. We need to remove this inversion. Okay, remove it. Yeah, swap operation. By intuition, if we apply the swap operation, we can fix it. This inversion is gone, right? This inversion is gone. So you can see we will get a solution that is based on swap operation. All right, so next, implementation idea. We remove all the inversions by local swaps. That's the, this one sentence, we describe the whole idea of this algorithm. Remove all the local inversions by local swaps. Okay? Yeah. Step-by-step procedure. Step 1, start from the first element for each scan. We scan from left to right. Okay? Start from the first element for each scan, going from left to right. Yeah. Do swaps one by one from left to right. Do swaps if necessary, right? So more precisely, when you see an inversion, what do you mean? What do you mean if necessary, right? When you detect there is an inversion, then you need to do a swap operation. If there is no inversion, go to the next adjacent pair and examine for the inversion and doing the iterations in that way. Now, step 2. Step 3, stop at the first in-place element. In-place element. Yeah. Because when you do swap, think about this. Swap operations, the first scan, you put one element in place, right? Okay, that element is already in place. Okay, one element in place. From left to right, you put the n element, last element in place. In your second scan, you should not touch that in place element, right? Already in place, why you touch it? Don't touch it, already in place. So you should leave that element in place alone, then work on the remaining elements. and you put another element in place, okay? Next round, cut off that in-place element, all the in-place elements, then do another scan, and so on, okay? So the step 3 tells us, do not do unnecessary operations. Yeah. So when you reach the first in-place element, don't stop doing any swap operation anymore, because those elements are already in place. All right, yeah. So next, now we want to, try to get the last round of understanding. Yeah. All right. From this whole procedure, you can see there is one element in place for every scan. The last element in the current array. Yeah. At the beginning, yeah. So when you do swap, or the last one must be the largest, right? Because every time when you do examine and swap, you will put larger element. You swap the larger element, to the later position, right? So another round, compare, swap, larger element to the, later position, and so on. Okay, all right, all the way to the end. So the last one must be the largest element, and you put it in place. Okay, yeah. In place. Yeah. All right, but not done yet. You need to start from beginning to end. Another round. And every time your currently processing array, subarray reduced by 1, size by 1. Okay. At the end, one element, do nothing. Just put it in place. You solve the whole problem. Okay. So that's the details, that kind of details. Yeah. Second, the in-place element of each scan appears at the end of the current array. Yeah. Yeah. The current array is a subarray that excludes all the in-place elements. Okay, yeah. So that's the, all the detailed information about this solution. Finally, let's summarize, several points of the solution. Visual imagination. Yeah. The swap looks like a bubble moving to the right, from left to right, the bubble. Okay. Yeah. So for that reason, we call it bubble sort. So this is an old algorithm we learned before, right? 2250, the old one. Here, I just repeat it. The reason is I want to explain we use multiple views on the same problem to get many different solutions. We use new way to understand that solution. Yeah. All right. And here, if we look at the efficiency of this algorithm, efficiency analysis is similar to that of the selection sort. Yeah, so if you do that, the formula you use similar to that of the selection sort. So I do not repeat it here. All right, yeah. But at the end, I want to ask you one simple question. What is the basic operation in the bubble sort? Remember, we have this concept, basic operation concept. But in this one, what is the basic operation? Here I give you two options, comparison or swap. In our discussion, we use swap a lot, right? Yeah. So our discussion focuses on swap operation. But actually, the basic operation is comparison, not swap. Why? because comparison happens everywhere. When you examine two adjacent pair, two elements, two adjacent elements. When you examine two adjacent elements, you always need to do one comparison, but you may not need to do a swap operation, right? Sometimes you need, sometimes you do not. That means the swap operation is not a basic operation. Comparison operation is the basic operation. Because if an array, given array already sorted, then you do not need to do any swap operation, right? There is no inversion. You do not need to do any swap. Okay? Yeah. You do not need to do any swap. Okay? So then, but you need to do many comparisons, right? Yeah. So in this way, you can understand comparison operation is the basic operation. All right, so let's finish D.1 right here.